Okay, let's begin. Yeah, this is the first and easy question. In the definition of a well order, we said that it should be a linear order such that every non-empty subset has a least element. However, we do not really need the part that it is a linear order. It is enough to assume that it is a strict partial order. Okay, so that's our first question. So if it is a strict partial order such that every non-empty subset has a least element, then show that it is a linear order. How do you approach this problem? You want to show it satisfies what? Trichotomy. Trichotomy is the only missing thing. So you are given any two elements A and B. What will you do?
Take the subset.
Yes. So we need to show trichotomy. Yeah, so let A comma B belong to W. We would like to show that A and B are related. Either A is equal to B or A less than B or B less than A. Okay? And A not equal to B. Consider the two element subset of W. Then it is non-empty. Then by that property what will happen? It must contain a, yes, contains a least element. And what will be that least element? If the least element is A, then A is less than B. If the least element is B, then B is less than A. So we don't really need the fact that it is a linear order. It can be derived from the well ordering property. Yeah, very simple idea. I just did not do this definition at that time because we had not discussed partial orders in detail. Any questions? This is the simplest exercise. Okay, let's do the second one. So say that a poset is bounded above if it contains a maximum element. If a maximum exists, then it is unique. And say that a poset is bounded below if it contains a minimum element. Okay. So and the poset is bounded if it has both a maximum as well as a minimum. Okay. So show that a finite lattice is bounded. How do you prove such a thing?
Take the join and meet of every element.
Yes. So let A1, A2, AN be all elements of P, of a lattice, maybe of a finite lattice L less than or equivalently. We are going to show that algebraic and order theoretic definitions of lattices are equivalent. Okay, so of a finite lattice this. Then consider A1 join A2 join AN. Now why can I write this expression? No, not just because it is finite. It is associative. That's why I can write this expression. Otherwise, otherwise what I have to do? I have to do something like this. Then first consider A3 and then dot 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 and then ultimately this. Okay. So by associativity and finiteness this will exist. Now this is a join, yeah, successive join, it's a finite join, so it must be an element of L itself, right? Use associativity. So maybe I am calling this particular element A naught, yeah. A naught defines by definition equivalence to this. Use associativity and conclude that AI is less equal A naught for any AI. How do you do that? By using associativity and commutativity also. I will show you how to conclude that AN is less equal A naught. What is A naught? A naught is equal to A1 join A2 and join AN. So there is something here, and then finally I should not write this bracket here, I should write the bracket just before that. So what is our definition of less equal in an algebraic lattice? So recall, x less than y, less equal y, if and only if x join y is y, if and only if x meet y is equal to x. Okay, so we know this. So A naught is this. So therefore AN is less equal A naught by definition of less equal. Yeah, AN join something is A naught. So we are done for AN. How do you do for AN minus 1, for example? You use commutativity. So you bring AN minus 1 at the end and then do the rest. Use associativity wherever required and so on and so forth. Yeah, I mean the finite join, I should also write this. Yeah, I mean finite join is an element of L itself. Correct? So therefore A naught is an element of L and every AI is less equal A naught. So what does that mean? It is the maximum element. Okay? And dually you can show it is the minimum element. So let me write something here, that if a lattice is bounded, then we denote the maximum by 1 and minimum by 0. And to emphasize this, we sometimes use the notation L, meet, join, 0 and 1. This is the complete signature of bounded lattices. So can you remind me what is a lattice homomorphism? Algebraic lattice homomorphism. It is a function that preserves, meets and joins. Now what will be a bounded lattice homomorphism? It is a function that preserves, meet, join, 0 and 1. All the properties should be preserved. Okay, so there is a difference between, so there could be some lattice homomorphisms between bounded lattices which are not bounded lattice homomorphisms because they do not preserve 0 and 1. Understood? Any questions about this? Okay, let's go ahead. Find an order embedding from omega plus 1 to the strict divisibility lattice of natural numbers. What is strict divisibility? That A divides B but A is not equal to B. We are going to denote this strict divisibility relation by divides the midline prime. Our usual notation is just divides. Okay, so can anybody tell me how to do this?
Take a chain with only two parent and then f of g of omega is 0.
Very good. So take any chain, yeah, and then what should be the topmost element?
0.
Okay, so consider a chain. I can start with 1. 1 equal to p to the 0 less than p to the 1 less than p square less than p cube and so on, and finally I will add a 0. Okay, for any p in n, p not equal to 0. I don't even have to consider a prime number. Yeah, this is still a chain. So then define g of n to be p to the n and g of omega. Yeah, omega is an element of omega plus 1. So g of omega to be equal to 0. Right? So this is our verify that G is an order embedding. What is the meaning of order embedding? An injective map that preserves and reflects. Yeah. So these numbers, if they are strictly they are related by strict divisibility relation, then their pre-images should also be related. Well, that's automatic, isn't it? Because the domain happens to be a linear order. So therefore we don't really need to check order reflection part. Understood? In this case. Okay, any questions about this? Then let's go forward. Now this is an interesting question. Yeah, suppose we are given a monotone function, then does monotone function preserve downsets under direct images and under inverse images? So let's first consider the inverse image. If dq is a down subset of q, then is f inverse dq a down subset of p? Yes or no?
Yes. Yes, sir.
Who is saying no? Yes. Give me an example. You want to write it? Who else thinks true or false?
It's true.
It's true? You want to write a proof?
Okay. Wait, let me write it down.
And what about the second statement? Is that true or false? False. Can you give me a counter example?
Yes.
Who can give me a counter example? Just one person or more? Okay, Sriram, you can come and write the counter example for 2. I will write the proof for this. What are you drawing? This is a post-it?
No, I meant
This is the eraser. Poset, the Hasse diagram for a poset cannot have flat lines.
Yeah, so
Okay, this is M3.
yeah. Yeah, so take like this or this, any one of those, and that's a downset A and 0.
A and 0 is a downset. It is a principal downset.
Yeah, and f of that is here, this, and that's not a downset.
That's not a downset. Correct? Because of incomparability, you can have something not good happening. So always remember that direct images are not well behaved, but inverse images usually are. So Sujal, you have got an example? Okay, so let us write down. So this is, one simpler example would be, you just consider a 2-element anti-chain and map it to 2-element chain. Yeah, this element is mapping here, this element is mapping here. Then this is A is a downset, but its image singleton 1 is not a downset because there is something below it. Yeah, you don't need any fancy examples also, you just need comparison of 2 elements. Okay, so let us write down a proof of 1. Okay, is F inverse DQ a down subset? Yes. So let X belong to F inverse of DQ. Okay, what do I need to show to prove it's a downset? I start with some X and I choose a lower bound for that, and Y less equal X. Y is a lower bound of X in P. Okay, then what will happen? Then F of X is in DQ by definition, and because Y is less equal X, then F of Y is less equal F of X. Since DQ is a downset, what do we conclude about F of Y? Yeah, Fx is in DQ and F of Y is a lower bound of Fx. So therefore, F of Y must be in DQ. And as a consequence, Y is in F inverse of. So done. Very simple proof. Okay, so 1 is good for every monotone map. We don't need any extra properties. Now let us explore what happens with 2 if we say that F is not just a monotone map but an order isomorphism. If F is an order isomorphism, then will the direct image of a down subset be a down subset? Yes, because, well, isomorphisms don't change anything. Yeah, they just rename elements. So for whatever happens here, the same thing happens there. How will you prove it? Follow your nose. Try to prove that, like the map is a bijection. Yeah, as long as you know that the map is bijection, you are done. Okay, but then we can ask the question, do we really need that it is an order isomorphism? Can we get away with something simpler. Let's say just a surjection, a surjective order preserving map, surjective monotone map. What do you think? Does a surjective order preserving map, surjective monotone map, preserve downsets under direct images? No. Why? If you say no, then there should be a counterexample. Yes, the same example. This is surjective, but it is not, but it doesn't preserve downsets under direct images. What if I ask you the same question for order embeddings? The answer is still no. Even for order embeddings, even if you have an order preserving map, why?
Let's say an example, like the 2 fire and
Okay, so one simple example would be, so I am just going to take these elements A, B and CD1, CD0. This is my codomain. A maps to C, B maps to D. This is an order embedding, yeah, because A and B are not related and C and D are not related either. This is an order embedding, but the image is not a downset. So order embedding, order surjection, nothing is enough. You need a very strong condition, namely order isomorphism. Okay, any questions about this? Yes, list all 5 element lattices. Has anybody done that? Yes, please come here and write them. So all 5 element lattices. Okay, so this is N5, that's a 5 element lattice. This is M3, that's also a 5 element lattice. Then this is just 5, 0, 1, 2, 3, 4, a chain, that's a 5 element lattice. Very good. Kite. Then inverted kite, that is also a 5 element lattice. And what else? See, what did we prove? That every finite lattice is bounded. So therefore the position of 0 and 1 is fixed. So you only need to worry about how 3 elements can be arranged. So either they are pairwise incomparable, in which case we get M3, then maybe 2 of them are related, the third one is incomparable, that will give us N5. If all of them are related, then that will give us a chain. If one element is related to both of them, then that will give us the kite or the inverse kite, reverse kite, and that's all. You are struggling to find another one. Okay, and now tell me which of these are distributive. Is N5 distributive? No. Give me a reason why N5 is not distributive. Which 3 elements can I choose to break distributivity? A, B and C, okay. So I can take A join B meet C. What is B meet C? B meets C is? No, B meets C is B. They are related. So therefore minimum is the meet. So this is A join B. What will it be? Correct. A join B is the least upper bound of both of them. And what happens with A join B? A join B and A join C. What is A join B? 1. A join C? So what is meet of 1 and 1? So where is distributivity failing? Maybe I should choose some different configuration. Which one? Should I just take this? What is A meet C? 0. What is B join 0? And B join A? What is B join A? 1. What is B join, maybe I wrote something wrong. B joins C? B joins C is C. So what is 1 meet C? There you have it. Okay, so N5 is not distributive. What about M3? Is M3 distributive? No. Yeah, we have seen that in the class. What about a chain? Is that chain distributive? Yes, every chain is distributive because it's just max and min game. Okay, what about the kite? Is that distributive? It will be, and the reverse kite will also be distributive. Okay, please check that. I am going to give you one definition at this point, and then Nupur will take over. So one definition, like an element A of a distributive lattice, distributive bounded lattice, perhaps I should also add 0 and 1 in here. Let me write it properly. L meet join 0 1 distributive bounded lattice is said to be complemented if there is some B in L such that A join B is equal to 1 and A meet B is equal to 0. A complemented element in a distributive lattice. Okay, so tell me, does A have a complement in N5? Yes. What is that complement? B is a complement and C is a complement also. Okay, I mean maybe I should say that the word distributive is not really essential for this definition. Yeah, this is not distributive, but there exists complement for A. For B also there exists a complement, namely A and C. Oh no, for B only A. But A can have multiple complements. In a distributive lattice, however, if the complement exists, then it is unique. Okay. On Monday we will start with this, yeah, the complemented lattices. What about M3? Does it have complements? Yes. What is complement of 0? Nothing? 1. Complement of 0 is 1, complement of 1 is 0, and it is always unique, then complement of A is B or C. Yeah, and similarly complement of B is either A or C. In a chain, yeah, let me call them A, B, C. What is the complement of A?
Does not exist.
It does not exist. Yes, a chain can never have complements apart from the minimum and maximum elements. What about the kite? Kite also doesn't have complements. See, this element, what is the complement of this element? Doesn't exist. Complement of this element and this element, none of them exist. Okay, so complements do not exist necessarily. Okay, so yes, I'm done over here. Nupur.
Also,
Yes.
so is there an example of a distributive lattice that has a complement for every element?
That will be called a bounded distributive lattice where every element has a complement is called a Boolean algebra. That will be our next topic.
Okay, so I am doing question number 6, where you have to show that the two definitions of a lattice that you've seen in class, the algebraic one and the ordered theoretic one, are equivalent. Which means that if you have the algebraic definition, then you can define an ordered theoretic structure on it which is consistent with what you already have, and vice versa. One note before I start, you have seen the symbols, these join and meet symbols used for both definitions, but because I'm using both of the structures here, I'm just going to use GLB and LUB for the ordered theoretic one to avoid confusion. We'll see that the concepts are the same at the end. But while doing the proof, of course, we can't use the same symbols for both. Okay, so let's look at the first part where we are starting from the algebraic definition and showing that showing an ordered theoretic structure that also forms a lattice. So suppose you already have a lattice, you define the ordered theoretic structure as A is less than or equal to B if and only if A meet B is equal to A. And now we have to show that all of the properties of the ordered theoretic lattice from this definition follow. So what do we have to show? First of all, we need to show that this boundary relation defines a coset here. So what are the three things you need for a coset? Louder, please.
Reflexivity, anti-symmetry,
And transitivity. Right. So let's start from there. Let A, B, and C be arbitrary elements. First, we show reflexivity. A meet A is equal to A, and therefore, I mean, this is obviously right. If it's not, then you can show this. A meet A is equal to A. Therefore, by definition, A is less than equal to A. Okay. Next, anti-symmetry. Suppose that you have both A is less than equal to B and B is less than equal to A. Then we will have that A is A meet B by definition here. By commutativity, we can switch their places, and then we can conclude, and we know that this is equal to B because B is less than equal to A, so by definition we have this. So we have that A is equal to B, anti-symmetry is satisfied. Next, we have transitivity. Suppose that we have A is less than equal to B and B is less than equal to C. Then you want to show that A meets C is equal to A because that will show that A is less than equal to C also, right? Okay, so you will start with A meets C. This A you can replace by A meet B because you know that they are equal because A is less than equal to B. Then by associativity you can change the position of the brackets. You get B meet C, which you know by definition from here is the same as B. So you get A meet B, which is the same as A by definition here. So we get that A meets C is equal to A, therefore A is less than equal to C, and transitivity is satisfied. So we have shown that this is a coset. Any questions?
I have a comment that you never use the join structure. Yes,
Oh, yeah.
so this can be done in a meet semi-lattice also.
Right. Now, let's come back to this later because of that comment. So we can show that we have, right. Let's look at the other structure. We will show that for every pair of elements, a greatest lower bound exists. We'll show that first. So let's suppose you have two elements A and B, arbitrary. So what is our candidate for GLB? We take A meet B, which is like, that is the notation you use for ordered theoretic definitions. So that should give you a hint that you probably want this to be your GLB. So first we have to show that this is a lower bound for both A and B. So you show that to show that this is less than, you want to show that A meet B is less than or equal to A, for which you need to show that A meet B meet A is equal to A. And you can show that by associativity and by commutativity. So you can switch the positions of these two things, and you know that this, by the absorption law, you have that this is equal to A. Therefore, you have that A meet B is less than or equal to A.
That's not absorption.
Oh, you're right.
That's just idempotency followed.
That is idempotency. I'm
Yeah.
sorry. This is not correct. So you have an intermediate step. And then this is equal to A meet B. Oh yeah, I'm so sorry. I showed the other. Yeah. So this is by idempotence. And this is associated. Right, so you get that A meet B is less than or equal to A. Now you exchange the positions of A and B over here. You follow the same argument. You'll get that A meet B is less than or equal to B. So A meet B is a lower bound for both A and B. Now we have to show that it is the greatest lower bound. What do we have to do then? How do we show that something is the greatest lower bound? Yeah, if anything else is a lower bound, it has to be less than or equal to a candidate. So suppose that you have a lower bound C. So C is less than or equal to A and C is less than or equal to B. By definition, you just write it like this. C meet A is C and C meet B is C. Now you have to show that we have to show that C is less than or equal to A meet B. So we start with this. Associativity, you switch these positions. Then because of this, you can replace this with C. Then C meet B from here is equal to C. And we have it. Which means that A meet B is the greatest lower bound here. So we have shown that the GLB exists and is equal to this. So the two concepts actually are the same. Okay, now I've left it for you as an exercise to show that the LUB exists. But for that you can just use the fact that instead of defining, this definition that A is less than or equal to B if and only if A meet B is equal to A, you can interchangeably use that A is less than or equal to B if and only if A join B is equal to B, which is what we have shown up here. So we show that from this definition, A is less than or equal to B if and only if A join B is equal to A, we can get that A join B is equal to B and vice versa. So let's look at what A join B is. A join B, we can just replace A by A meet B because A is less than or equal to B. That's our assumption for the first part. And then we have by absorption, this is absorption, this is equal to B. Conversely, suppose that A join B is equal to B, then we have to show that A is less than or equal to B in this order. Then A meet B, we can replace B by A join B, and we get it again by absorption. Which means, in fact, right, we've gotten something nice for a lattice that A join B is equal to A if and only if A meet B. Sorry, A join B is equal to B if and only if A meet B is equal to A. Is that fine? Okay, stare at this for a minute maybe. So now you can use that definition to follow the same argument as we did for showing that the GLB exists, to also show that the LUB exists. So that I've left for you as an exercise. And we have verified all the properties of that you need for the order theoretic definition of the lattice to whole. Therefore, we have defined an order theoretic lattice structure starting from an algebraic lattice structure. Any questions? Okay. Now we have to go the other way around. We have to go from the order theoretic definition to the algebraic definition. Suppose we have an order theoretic lattice. We need to define these two, what these two operations do. Again, we go by our intuition and set, actually just following that same argument there, we set A meet B to be the GLB of A and B, and A join B to be the LUB of A and B. And now we have to start verifying that these operations actually fit that definition, the algebraic definition of the lattice. So yeah, you show commutativity. I've left that for you as an exercise. You have to show that the GLB of A and B is the same as the GLB of B and A. Trivial, but it helps to write it out. So that is an exercise for you. Then associativity. How do you show associativity? Well, first of all, how do you write A meet B meet C? This just becomes GLB of A and B, comma C. And then you just proceed. So the way I have done this is, I assume that if you have D is less than equal to GLB of A comma B comma C, then I have just gone from here to show that this is equivalent to saying that G is less than equal to GLB of A comma GLB of B and C. And you just use the definition of GLB to arrive at this statement, from which you can go backwards to get here. Yeah.
How can you say like D is less than B less than equals to B and D is less than equals to C? This implies D is less than equals to GLB of B and C.
That's the definition of GLB, right? If you have a lower bound for both of these, then it has to be less than or equal to the greatest lower bound. What is the definition of a lower bound?
Common lower bound.
Yeah, common lower bound. So if we have that B is less than equal to A and D is less than equal to B, then we have that D is less than equal to the greatest lower bound of A and B. Okay? So you just replace your A with this and your B with C here. Fine? Right. So you follow that argument backwards and then in reverse, and we get that these two statements are equivalent. Now this is for an arbitrary D, and this holds for, an arbitrary D. Now what do? You set your D to be this first thing. So you know that GLB of A comma B comma C is less than equal to itself, and therefore putting the same D here, you get that it is less than equal to the second thing. And similarly, you set your D to be this term. You know that this relation is satisfied. Therefore, this relation is satisfied. And you therefore get that these two expressions are equal. Fine? So you have that they are equal. Therefore, this is just a way of writing this. This is just a way of writing this. We have shown associativity. Similarly, you have to show, I've just shown it for meet, you have to show it for join. Same arguments are going to work. Then we just have two things left. Idempotence, which is pretty trivial. A meet A is the GLB of A comma A by definition, which is equal to A. Do a D for join. Then absorption also follows similarly. This entire proof is just using the same things over and over again. For absorption, you have to show that its expression is equal to A. So you just write out the definition, and then so that I didn't have to write something ugly like I did in the previous thing. I just said this is equal to C. So by definition of GLB, we have A is less than equal to A, and we have A is less than equal to C by the definition of LUB over here. Now suppose, our candidate for this entire expression is A, of course. We have shown that A is a lower bound for both A and C. We have to show that it is the greatest lower bound. Suppose that you have another lower bound, common lower bound for A and C, then that lower bound has to be less than equal to A, because like I literally just copied the statement again. I don't need to, which means that A is in fact the greatest lower bound, and we get that this expression is equal to A. Any questions?
I have never seen this proof in such a detail.
It's a very simple proof.
Yes.
But you need to be, when you're writing a proof as simple as this, you need to be very clear about what properties you're using in each step. Right. So we have shown that both the definitions are equivalent. Modulo, you're showing the same things for John. I've already shown.
Yeah, so has anybody done this exercise? Hasse diagram for divisors of 60, proper divisors of 60. Yes, you want to draw it? You also have done? You can do the 24, yes. Only 2 people solve exercises before coming to the class. So, for those who do not solve any exercises, it's just like another lecture. Here is a problem, here is a solution. Yeah, it's theory. When do solutions make sense in the class? If you tried, you failed, or you succeeded, but there is an alternate proof in the class, done in the class. If you struggle with a problem, then only somebody providing you with a hint or a solution makes sense. Otherwise, it's just lecture.
Should I draw the, because
yes,
okay.
That was the important part. One, where is one?
Proper divisors.
Proper doesn't mean one is missing. Proper means 60 is missing.
Okay.
Very good. What are the maximal elements? I don't want you to draw these pieces.
Yeah.
What are the maximal elements in this?
12, 13 and 20.
Yeah, you understand? Yes, 24 you want to draw? I think the question was draw the inverted lattice for 24. You want a new page? We are going to go a bit over time today. Just to maybe just give them a sketch of the proof. Nupur? Yeah?